Okay, so picture this. You've just been handed the reins at Newark Airport's air traffic control.
Okay, high pressure job.
Totally. The radar's buzzing, planes everywhere, taking off, landing, and your number one job, the absolute critical thing, is making sure no two planes try to occupy the same bit of sky or ground at the same time.
Pretty stressful, right?
It definitely highlights a massive coordination challenge. Very real world, very high stakes.
Absolutely. And, it turns out this kind of problem, making sure things don't collide, it's something mathematicians have actually been thinking about for a long, long time.
Right. They like these kinds of puzzles.
Their approach, it's kind of cool. They take that super complex reality, all the runways, the taxiways, the flight paths, and they simplify it. They turn it into an abstract map, what they call a graph.
A standard tool in the toolkit.
Yeah. So like every gate, every intersection point, that becomes a dot on this map, a point. And every possible route a plane could take, that's a line connecting those dots. It's a really clever way to strip out the physical noise, you could say, and just focus on the connections, the potential conflicts. Gets right to the heart of the who is where when question.
Exactly. So the real challenge then is, okay, how do you schedule all these routes, all these lines on our map so you never have two planes at the same point at the same time?
Right. The core scheduling problem.
And the solution they came up with is pretty ingenious. It's like giving each route a different color, and each color stands for a specific time slot.
Okay. Like red means 9:00 a.m., blue means 9:05 a.m.
Something like that, yeah. And the absolute golden rule is any single point on the map, like a runway intersection, all the lines connected to it must have different colors.
So different colors mean different times.
Exactly. Which means no two planes get scheduled for the same spot at the same time. Collision avoided. Phew.
And this idea, graph coloring, it's actually a really fundamental concept in computer science and in math. It pops up all over the place, Helps with resource allocation, scheduling conflicts, tons of stuff.
Right. Now, you can probably imagine if you have a tiny little airport map, maybe 10 gates or something, you can maybe figure out the colors with some pens, right? Sit down and work it out.
Yeah, for a small graph, you could do it by hand.
Maybe. But think about a huge international airport. Or forget airports. Think about scheduling tasks for thousands of computers in a network. You end up with these massive graphs, billions, maybe trillions of connections.
Way too big for colored pens.
Oh, way too big. So that's where computer algorithms come in. These specialized programs designed to solve this coloring problem automatically. But here's where the story gets kind of stuck. For the last 40 years, 4 decades, according to Separ Asadi, a computer scientist, the speed of these algorithms, how fast they could find a valid coloring, it just hadn't really gotten any better.
Wow, 40 years is a long time in computing.
Right. He basically said they were, quote, stuck.
That really suggests a fundamental challenge, a real bottleneck in the field. When progress stalls like that for so long, it often means you need a totally new idea to break through.
Which, conveniently, brings us to the exciting part. Just this year, 2024, suddenly, 2 separate research groups announced they'd developed much, much faster algorithms for this exact problem.
Oh, interesting. 2 independent teams.
Yeah, like a log jam just suddenly burst.
That's often a sign something significant is happening, a kind of paradigm shift maybe, when multiple people hit on it around the same time.
And wait, it gets even better. There's another new paper. It's going to be presented next year, 2025, at a big computer science conference. And it describes an algorithm they're calling nearly optimal.
Nearly optimal. Okay, that's a strong claim in algorithms research.
Sounds like the holy grail, doesn't it? Like practically as fast as you could possibly hope for.
Well, yeah. In computer science terms, nearly optimal usually means its efficiency scales incredibly well. It's really close, maybe just off by a small logarithmic factor from the absolute theoretical speed limit for that problem.
Okay, and here's the really wild part, the mind-blowing bit. This new algorithm's speed, it barely depends on the size of the airport, the number of points on our graph.
Wait, really? Not the number of gates and intersections?
Nope. It almost entirely depends on the number of flight paths, the number of lines.
Huh.
So whether you've got a tiny airstrip or some mega hub like O'Hare, the hard part for this algorithm is mostly just how many routes you need to color, not how many places those routes connect to.
That's genuinely a profound shift. Historically, these graph algorithms, their complexity, it's almost always tied to both the number of points, the vertices, and the number of connections, the edges.
Right.
So an algorithm that mainly scales with just the edges, the connections, that could be dramatically faster for a lot of real-world networks, because many networks are what we call sparse. they have relatively few connections compared to how many could exist.
Exactly. And just to hammer home how big a deal this is, Anton Bernstein, he's a mathematician at UCLA, he said this new paper almost completely solved the problem.
Wow, almost completely solved.
Yeah.
Quite a statement.
Yeah. He even called it a milestone few would have predicted even a couple of years ago. That's not just, a nice comment. That's declaring a major breakthrough.
Bernstein saying that really underlines how unexpected and transformative this result feels to people in the field. It suggests a problem many thought was just fundamentally hard has suddenly seen a solution that seemed, well, years away, maybe decades.
So that's what we're going to do in this deep dive. We want to unpack this mathematical breakthrough, try to understand why it's causing such a stir in graph theory, and, explore what it might mean for the real world. These super fast algorithms, what could they actually do?
Sounds good. Where should we start? The history.
Yeah, let's dig into that. This problem, efficiently coloring these graphs, it didn't just appear out of nowhere, right? When did mathematicians first really tackle this?
Absolutely. It has a history. The real groundwork was laid way back in 1964. There was this brilliant mathematician, Vizing.
Vizing, okay.
And he proved something pretty remarkable, actually. He showed that figuring out the absolute minimum number of colors you'd ever need for the edges of any graph is, well, surprisingly straightforward.
Oh, yeah. How so?
You just find the point, the vertex, that has the most connections coming out of it. The busiest intersection, let's say.
Okay.
Count those connections, add one, that number. It's guaranteed to be enough colors. Always.
Whoa, wait. That sounds almost too simple? So if the busiest gate at Newark has, 15 taxiways connected to it, you know for a fact you'll never need more than 16 different time slots or colors for the whole airport schedule.
Precisely. Vizing's theorem gave us this really crucial theoretical ceiling, a guarantee on the number of colors. But, and this is a big but,
It's always a but.
the real challenge wasn't just knowing how many colors you needed, it was figuring out the actual assignment. How do you efficiently give each edge, each flight path, one of those colors while respecting the rule at every single point?
Okay, so it's like knowing you need exactly 10 boxes for moving versus actually figuring out how to pack everything neatly into those 10 boxes without breaking anything.
That's a great analogy, exactly. Knowing the number is one thing, efficiently finding the coloring scheme is another beast entirely.
Right. So Vizing figured out the how many, but did he also have an algorithm for the how-to?
He did. He provided an algorithm, but as we sort of hinted at earlier, it wasn't super fast.
How slow are we talking?
Well, its runtime, the time it took a computer to run, was related to both the number of connections, let's call that M, and the number of locations or vertices, call that N. It was roughly proportional to M times N.
M times N. Okay. So for a huge airport with lots of gates N and tons of routes, that multiplication gets big fast.
Gets very big, very fast. It could take a really, really long time. Impractical for large-scale problems.
And the sources mentioned some improvements happened later, in the 80s.
Yeah, there were some steps forward then. Researchers managed to tweak things and reduce the dependence on N, the number of locations. Instead of being proportional to N, it became proportional to the square root of N. So M times square root of N.
Okay, square root of N is better than N, but still, if N is massive, its square root is still pretty big.
Exactly. It was an improvement, definitely. But the size of the network, the number of vertices, still played a significant role in the runtime. And, well, after that. For the next, almost 4 decades, making substantial progress beyond that M times square root N barrier proved incredibly difficult. People were really stuck.
Which just makes this new result, this nearly optimal one, seem even more dramatic. The fact that it basically gets rid of the N dependence almost entirely.
And focuses mainly on the number of connections.
That's the fundamental shift, isn't it? It changes how we can even think about tackling these huge scheduling puzzles computationally.
And what's really exciting now are the potential real-world consequences. Ben Azad, one of the researchers, makes a great point. He says that theorists, we often ignore constant factors in algorithms. We look at the Amen or the bottom part, the overall scaling trend.
But in practice, for actual applications, those constant factors can make a huge difference in actual speed. A theoretically fast algorithm might still be slow if the hidden constant is large.
Okay. So how does this new one stack up?
Well, the runtime for this new algorithm is technically proportional to log for number of connections times the logarithm of the number of connections. But Crucially, Benesod notes that the constant factor hiding in there seems to be remarkably small.
Ah, so it's not just theoretically good, it might actually be fast in practice too.
That's the hope, and the initial signs look promising. It suggests we might actually see real, tangible speed-ups when applying this to practical problems. Okay, that's huge, because sometimes these theoretical breakthroughs, they're amazing on paper, but they don't quite translate to real-world speed because of those hidden costs or complexities.
Exactly. But this one seems like it might deliver. And, the researchers aren't stopping here. They're already looking at ways to push it even further.
Oh, yeah. Like what?
Well, one big goal is to get rid of the element of randomness that's currently part of how the algorithm works.
Randomness. Why is that in there, and why get rid of it?
Sometimes using randomness can help find solutions more quickly on average, but it means the runtime isn't perfectly predictable. Occasionally, by chance, it might take longer.
Okay.
So eliminating that randomness would make the algorithm deterministic. You'd get a more consistent, guaranteed runtime every single time. And for critical things like our air traffic control example, predictability is really important, right?
Absolutely. You don't want your safety system having a slow day just because of, like, a bad coin flip inside the computer.
Precisely. Reliability is key. The other main goal, which Asadi highlights, is getting rid of that lingering logman factor in runtime.
So going from logman down to just...
Exactly. Achieving what's called linear time complexity, where the runtime is just directly proportional to the number of connections. And that's it.
And that's like the ultimate goal.
For many graph problems, yes. Asadi basically says that achieving linear time just proportional to m is often considered the best one can hope for. It's like the theoretical speed limit for processing the input.
So they're really shooting for the stars here, trying to reach peak efficiency.
They are. It's ambitious. And Robert Tarjan, another big name in algorithms, he acknowledges that, yeah, people definitely want to remove the randomness in that log term. But he also stresses that it's likely going to be really, really hard. There are significant technical challenges.
So maybe not tomorrow.
Probably not tomorrow. Tarjan predicts that this current nearly optimal result, the m-logma1, is likely to be the state-of-the-art for the foreseeable future. It's such a big leap forward that surpassing again might take quite a while.
Gotcha. So it feels like we've witnessed this jump from decades of kind of stagnation to a massive breakthrough. And even if there are still tiny theoretical improvements possible way down the line, this current algorithm is pretty much a game changer for coloring these complex graphs.
I think that sums it up well. We started with this very concrete image air traffic control, preventing collisions. And we saw how that translates into this abstract mathematical world of graph coloring. We tracked the history, the long period where progress was slow, Vizing's early work, the M and M-Screen algorithms, and now suddenly this near-optimal solution that changes the game by focusing almost entirely on the connections, not the size of the network.
So listening to this, what should you take away? Well, maybe think about all the other incredibly complex systems out there, things you interact with every day without even realizing it.
Like what?
Well, global shipping networks, right? Getting packages from A to B, or the internet, how data flows, even things like social networks, how information spreads. All of these can be modeled as graphs.
Absolutely. Nodes and connections everywhere.
And this breakthrough, it suggests that maybe the underlying math, the structures controlling these massive complicated systems, might actually be more manageable, more efficient than we thought, thanks to theoretical leaps like this one.
It definitely opens up possibilities.
Yeah. It really makes you wonder, doesn't it? What other huge, seemingly impossible problems out there, problems that seem totally intractable right now, what if they're also just waiting for the right mathematical insight? What else might be on the verge of a similar, near-complete solution? Makes you think.